Thank you, and welcome everybody. So I've prepared a couple of slides about Lancaster, so you get an idea where we're coming from. But I thought rather than me talking a lot about, great research areas and so on, it's probably better to show an example. So Hamish kindly agreed to get up early today. I think he's already in the office. It's 7 o'clock here. And he's going to give an overview on one of our current projects. So I'm just going to share my screen. So my name is Anna-Lena, and I'm a senior lecturer in predictive analytics at Lancaster University. And I joined almost 4 years ago, and I've been to a couple of other universities before. So there are lots of things that I appreciate about Lancaster and why I like being here. And I'm trying to convey that in my talk, but I'm also really happy if you ask any questions, so feel free to interrupt me at any time. So Lancaster is located in the northwest of England, so that's very close to Manchester. And we are also very close to the Lake District, which is great if you like nature and hiking. It's a bit more than a 2-hour ride on the train to London and Edinburgh, so it's also good for city trips, but it's more of a rural location, and mostly if you like nature, there are lots of opportunities around here. We have about 17,000 students on our campus, so it's a rather big campus, also with many restaurants and cafes. And rather than showing you all the great rankings of the university, I thought I'd just emphasize the role of research that's quite important in Lancaster. The management school, for example, was ranked first in the UK for research power in the REF. I don't know if you know the REF, that's like the research excellence framework, where different universities in the UK compare with each other on different dimensions. And I think it's a great location, but for me, the main reason for coming here was the focus on research. And in the management science department, we have more than 50 academics, and we're working in different areas. So we have people in operational research, information systems, and operations management. So that's quite a spread. The people in operational research focusing on quantitative methods, whereas those in operations management rather focus on qualitative methods. But very often when we talk to companies, they say, okay, that's a great approach. We would really like to use that if we suggest a model. But then they're like, okay, but how can we actually put that in practice? How can we make sure that people interact with that they like to have a dashboard, and then it comes to usability, for example, and then we can direct them to our IS people, and they are then interested in those aspects. So there is a lot of collaboration going on, but also if we talk to companies, it's good to know that there is somebody in the background who can do something else, and different expertise in different areas. We also have different research centers. So we have the Center for Marketing, Analytics and Forecasting, where we mostly focus on forecasting demand. So we look at different types of business decisions, and we work with many different kinds of companies. So for example, we're working with automotive companies, retailers, basically anybody who has some forecasting issues, which many companies do. We also look at forecasting intermittent demand. So for example, if you have a part like, an engine or so as a spare part of which you don't sell that much, and you sell it in smaller quantities, then you can use different forecasting techniques to take the structure of the problem into account. Part of that center is also inventory optimization. So we work with different companies to help them make better inventory decisions. And that's also the main focus of my own research area. So I work a lot with retail companies, for example, where we look at how they should make inventory decisions, like very specific examples like strawberries or bananas. And then we look at how they actually made those inventory decisions and analyze, why they did better or worse than what a mathematical model would have told them to do. We have also a center for productivity and efficiency. And in that center, we are also looking at technology adoption and productivity, supply chain productivity. And we work a lot with SMEs. So SMEs is something that Lancaster University is also quite keen on to collaborate with. And yeah, then we also have the Center for Transport and Logistics, where we do lots of different projects that have to do with transport or logistics of any sense. So for example, aviation and air transport. So we work a lot with different types of airports or airline companies. Also emergency response logistics, last mile logistics, lots of different research areas. Methodology-wise, there is also quite a big spread. So we have some people who are mostly focusing on deterministic problem, and then we have also a large community of people who focus more on stochastic problems. Some people work on multi-objective optimization, which I think some of you do as well, according to the projects that I've seen on your website. Then also combinatorial optimization. We do have colleagues in this area. So there is quite a big spread on those topics. And I'm really happy if you want to have a look at our website as well and basically look at what the different colleagues are doing. So we also have Doctoral Training Center. This is funded by EPSRC, and it's called STOR-i. And STOR-i stands for Statistics and Operational Research in Partnership with Industry. So there is a clear focus on working with industry on problems that are motivated by practice. Also, what is quite unique about the center is that it's a collaboration between colleagues from statistics and people from operational research, which means that we have many interdisciplinary projects. So, for example, I'm working currently on a project where we look at inventory management for end-of-life products. So when a product gets to the end of its life cycle and the company wants to stop selling that, and then we want to determine how many items should we still keep in stock, knowing that we won't be able to sell those products at some point. And we're planning to combine that with change point detection. So we have a colleague involved from statistics who is an expert on change point detection. So all the training and the PhD projects are led by staff both from management science and the Department of Maths and Stats. And we work with many different companies. Basically 80% of the projects are done with a partner from industry. And if you decide that you would like to visit Lancaster at some point, then you would be based in the office with the STOR-i PhD students and collaborate with one of the colleagues from the management science department. So this is just a screenshot from your website. So if you're interested in coming here, then please just let us know. And then we would make sure that you get in contact with one of those colleagues. And I've just had an email exchange with my optimization colleagues over the last week, and they're all very keen to get to know you as well. Okay, I'm just going to pause here in case there are any questions.
Does anyone have any questions at this point for Anna-Lena? That's a great acronym, Anna-Lena, for Central. We like a good acronym around OPTIMA. I'm quite impressed by that one. We also have quite a few people here working in transportation and logistics. Is that so? You're more of an inventory person, but there you have a good number of sort of operations research, transport, logistics people over in Lancaster as well.
Yes, and I've shared the website of OPTIMA with them last week, and they recognized lots of names, and they were like, "Oh, this is really interesting." So we would love to collaborate with some of you. So yeah,
great. Okay. So now we're going to hear from Hamish.
Yeah, so hi, my name's Hamish. As you can probably hear, I grew up in Australia and then I came over here for the PhD. So if anyone has any questions about what it's like coming from Australia and moving over to Lancaster for a bit, I'm happy to give my email address to Kate to pass on to anyone. So this is just, I'm just going to talk here about one of the parts of my PhD I've been working on. So obviously, as you know, I've been supervised by Anna, but this is also some work with Jamie Fairbrother, who's involved in stochastic programming, which you'll hear about in this, as well as some like not quite transport logistics planning, but some flight planning, and John Boylan, who's in the area of like forecasting. But so today what I'm talking about is scenario reduction methods in stochastic programming using what we call the recourse space. So our motivating example for this is looking at staffing a mail center. So when mail is getting sent around the country, it's got to pass through a lot of different like facilities along the way, but the main sorting areas are these places called mail centers. So they're these big facilities with lots of different machines and people doing lots of different jobs. And so what will happen is that mail comes in unsorted here and it'll enter through like a bunch of trucks. If you see my screen, I do apologize, the motion sensor light cuts out in here a bit. So I've gone black, but I'll just push through. So the mail comes in on these trucks, and then it's going to pass through a number of these different sections here called work areas. Now, each work area's got a specific job. So some of the earlier ones will just be sorting letters from parcels, or sorting like small standard size envelopes from flats, which are bigger size envelopes. Some of them will be just literally turning and stacking all the letters, for example, so they all face the same way. So they can be fed into these big sorting machines, and then these sorting machines will start splitting them by destination. Then you have some which is you're gathering the mail that's going on to a different mail center. You have some which is gathering mail that's staying here, and it starts ordering them literally in the order in which a post officer will put them in the letterboxes. And so there's a variety of, so it's going to pass through a number of areas. Eventually they'll end up sorted and they end up back on the trucks going back out. Now, there are a lot of different types of mail that come in here. So you have letters versus parcels, but within that you have, you know, overnight deliveries, 48-hour deliveries, standard envelopes, flats, regular size parcels, different size parcels. So there's a lot of different types of mail, and they've all got to pass through these different mail areas in different orders in order to get sorted. Now, while machines are used quite a lot, the machines need to be operated by staff members, and there are some work areas which are manual sorting. So you need staff members to put into these work areas. Now, this is a bit of a balancing act for management here, because on one hand, the more staff you put in, the more mail can be sorted through a work area in a given time period. So the throughput gets a bit higher, which is good because obviously there are targets in how quickly you've got to deliver the mail. Like, so for example, you know, your overnight mail deliveries have to be delivered overnight. So you sort of have to get through that. Having said that, the more staff that you put in here, obviously the more that costs the company that's doing the mail sorting. All right, so you've got this balance. It's the standard operations research balance of you want to have lower costs, but you want to meet certain standards. So if you know the required mail before you've got to set these staff levels, you can set this up as like a network flow model, which, you know, a little simple one here. These are names of different work areas. You have a source and a sink, and you can solve this using a network design problem. And that's sort of some earlier work that we've done in the PhD. But yeah, and so that's straightforward is the wrong word, but like it's sort of, if you know about network design models, there's not that many tricks to it. It's sort of doing that. However, if you have to decide your shifts before the mail volumes are known, so often you've got to set your shifts and how you can staff these work areas a week in advance, but you don't know for certain what the mail volumes are going to be until maybe the day of or the day before, then you've got to use some different techniques. This is quite common in optimization, having to make a decision before you know all the information. And one way you can do this is through stochastic programming. So in stochastic programming, we're going to split our problem into our first stage decisions, which are decisions that you make initially. You're then going to get some unknown information, and then you're going to make some second stage decisions, which are decisions you make in response to learning what this unknown information is. So in this, what you want to do is you want to minimize the cost of your first stage decisions but you also want to minimize the expected cost of your second stage decisions, given what your first stage decisions are made. These are called recourse costs. So in our example of staffing a mail centre, our first stage decision are how many staff members we're going to put on. Our random variable, our unknown information, is how much mail is going to arrive during the shift. And then our second stage decision, that could be a number of things. That could be maybe you've got some staff that you can bring in like on short notice, but that will cost a bit more. So you can do that to plug the gap. Maybe you can get your staff to stay later and sort of pay them sort of some overtime. Maybe you're allowed to have some letters be delayed or like miss their target, but there will generally be a cost associated with that. And so our recourse cost is the cost of what these second stage decisions are going to be. All right. More formally, because you are all operations research students, I can write that, you're going to write this as something like this. So you want to minimize over some feasible region, some function of your first stage variables. So your Y are first stage variables with some cost function associated with them, plus this expected value of Q, which is your recourse function. So that's the cost of taking action X given your first stage decision variable and given whatever realization of the unknown variables you've got psi. And psi, we assume, has some distribution. Generally, you have a bit of an idea about the distribution, or you like, so for example, with the mail example, you have forecasts of what the mail are going to be, but you know, there's uncertainty around that. So this problem can quite quickly get quite ugly, particularly with this expectation. So we make a few assumptions. Firstly, we're going to assume that F and Q are linear because, you know, that's always fun. That's always easy. Makes the problem a lot simpler. We're then also going to approximate our distribution P with P dash. We'll say P dash is discrete with a set of scenarios S and associated probabilities PS. Therefore, we can approximate this expectation by just taking the discrete expectation with respect to P dash. And then you'll notice that now, because these are all, if Q is linear, and this is a linear combination of them, and F is linear, this just becomes a linear or mixed integer program. And, you know, we've got algorithms to do that. We've got solvers to do that. And that's all well and good. So, you know, you might think, oh, okay, well, this is just a linear mixed integer program. Okay, so, you know, what's the issue? Well, there's kind of a fundamental problem with stochastic programming, and it sort of boils down around the scenario set. So down here, you have a scenario set of just one scenario. And down here, this is as your scenario set size grows. So obviously, due to like the central limit theorem, the more scenarios you have, the more accurate this scenario set's going to be. But you kind of end up, to calculate this recourse cost, you kind of end up solving like a stochastic like a linear program across all of these scenarios. And because you've got the same first stage decision variables for each scenario, they're all linked together, so you can't sort of break that down. So quite quickly, as it goes up, it becomes less tractable. So this is kind of what the go is with stochastic programming is you want to find a scenario set that's small enough it's still tractable to be solved, but like large enough or representative enough that you're accurately covering the uncertainty associated with these random variables. Excuse me 1 second. So there's currently two broad schools of thought on ways you can do it. One school is sort of to use what is called scenario reduction methods. So this is when you take a large scenario set and you just reduce it down. So the first and most obvious one is just randomly sampling from this. This is generally used as like a baseline method to compare how other methods go. Obviously, there's clustering. So if you can cluster your scenario set and then take like a representative scenario from each cluster, that can reduce it down. You can do some dimensionality reduction techniques. So some authors look at using PCA or SVD to do this. And then one of the authors, Dupakova, has sort of in the area reasonably famous backwards reduction and forward selection method. And this involves looking at like pairs of scenarios that are quite close together and then taking one of those and keeping that in the scenario set. The other method, which I won't talk about too much today, but it's quite common, is scenario generations. This is more like you sort of start with a set that's empty and you build up a good scenario set. So one thing is moment matching. So you can sort of generate a scenario set to have specific properties. So it's given mean and given variance, given skewness. So Hoyland's done some work on that. You can also match copulars in your scenario sets. That's matching some higher order dependency structures. That can get quite good if you've got some like multi-dimensional scenarios. And then there are various other sampling methods. There's antithetic sampling, Latin hypercube sampling, importance sampling. So these exist outside stochastic programming, but people have all used them quite a lot for these sort of things. There's another classification on scenario stochastic programming methods that we need to look at as well, which is whether it's distribution driven or problem driven. So initially, distribution-driven methods are you create a distribution of scenarios that match some properties or some target distribution. So in this, it's like, okay, so we're going to ignore what our problem is for now, and we want our scenario set to, for example, be like a normally distributed scenario set. So then you say, okay, we're going to generate one with like, you know, a given mean, given variance, and things like that. What's becoming more common now is to, rather than ignore the problem that you're solving while generating your scenarios, is to like consider the problem while you're doing it, because then maybe you can match your scenario set to a given problem to make it a bit easier. So for example, Jamie Fairbrother, who's one of my other supervisors on this project, he's done a lot of work saying that if you do different risk measures, you should generate the scenario set in different ways. So for example, he did a lot of work on conditional value at risk, which is trying to, instead of minimizing just the expected recourse cost, it's minimizing the expected recourse cost in the worst 5% of cases. That's just saying, let's not have a very bad catastrophic loss. And so in that, what he discovered is basically you should be generating all your scenarios to be in that tail risk region. There's no point generating it across the whole space. So a couple of other authors have done clustering, but instead of just looking at the distance between scenarios as a distance metric for the clustering, they do an opportunity cost measure as the distance. So that's the distance between two scenarios, is how bad the recourse is if you prepare for scenario A and get scenario B. So that starts looking at how sort of similar they induced solutions are. And then Ben Narum, who another student, Jamie supervisor in Norway, has measured how various scenarios perform given various candidate solutions before applying the SVD. And so this is an interesting idea that we're going to look at a bit more. So I've talked a lot about this problem-driven scenario generation, but you might be asking, you know, why go to all this trouble for it? Well, so if you think about it intuitively, scenario reduction methods are often based on the distance between two scenarios. And the key assumption is that if two scenarios are similar to each other, then they require similar first stage decisions. So back on a mail center example, you might think if you get 2 days with similar mail volumes, you know, you need similar staff levels for it. Now that sounds quite intuitive and that sounds quite sensible, but in practice, does it work? So if you can imagine a simple mail center. So in this, we've only got 4 commodities. We've got first and second class letters and first and second class parcels. And we've got 2 work areas, 1 work area to sort letters and 1 work area to sort parcels. And then you can put workers in either work area, and each worker can sort 2,000 items per day in either work area. All right, so now we're going to consider 3 different days. So on the first day, you get 10,000 letters and 4,000 parcels. On the second, first class letters and first class parcels. On the second day, you get 9,000 second class letters and 4,000 second class parcels. Day 3, you get a mix of both. Okay. Now let's say we only wanted to pick 2 of these days for our scenario set, and say we want to do this by clustering. All right, so firstly, what you do is you calculate the distance matrix between this. So this is the Euclidean distance between the days. So you can see day 1 and day 2 quite clearly the furthest apart, day 3 sort of in the middle. All right, so if you're going to cluster them, you put day 1 in one cluster, day 2 in another cluster, and you put day 3 in one of them. You probably put it with day 2 because it's a bit more similar. All right, and then that sort of seems similar, seems sensible. But now suppose we've got 7 workers, and recall each worker can sort 2,000 items per day. And let's say we put 5 workers to sort letters and 2 workers to sort parcels. And we're going to say the recourse cost is how many items are left over at the end of the day. So we're just going to sort of test this out and see how it goes. Well, you can sort of see with day 1 and day 2, we have 10,000 or 9,000 letters. So our 5 workers can sort all of them. So we have no leftover letters. We have 4,000 parcels, and our 2 workers can sort them, so that's fine. Day 3, all the letters are going to get covered because we've got 10,000, 5 workers, that's fine. But we now got 5,000 parcels. We can only sort 4,000, so we're going to have 1,000 parcels left over. So you can see if you look at the recourse, like if you don't care about the actual data, but if you look at the recourse, day 1 and day 2 are clearly the most similar, like they're identical, despite the fact that they were furthest away in their original space or the scenario space. All right. So just to show this point graphically, I'm going to really hammer this point home over the next 6, 7 slides. Say these are sort of taken from one of the problems we use later, but say you can view it as different types of letters. So say this is one type of mail and another, and this is say a day that's got 15 first-class letters and 23 second-class letters. We're now going to transform it to what's called the scenario space. So what we've done here is we've given a candidate solution, and for each scenario, we've worked out for each candidate solution, this is one solution, and this is a different solution, worked out what the recourse is going to be. So you can sort of think of this as this is like a staffing plan. So this is, we've put 5 workers and 2 workers in the letters and parcels area respectively. This one might be, we do 3 and 4, okay? And now each dot here is the recourse cost for one scenario with each their candidate solution. So this might be a scenario which with our first set, with our 5 workers and 2, you have about 20 letters left over. And then it's about 0 letters left over on our second set. So kind of this is the recourse space. Now you recall that the recourse space is kind of what we're trying to estimate in our stochastic program. So this is really the area that we want to sort of be representing with our scenario reduction. So now say if we cluster our scenarios based on just how far away they are, in our 2 clusters, I mean, comes out quite obvious, right? So you have sort of split in 2. The blue dots are all reasonably quite similar. The red crosses are all similar. If you pick like the medoid scenario of them, it's quite representative, it's quite in the middle, all right? But if we apply these clusters to the recourse space over here, you can see now they're all mixed up, right? So now these blue scenarios aren't actually representative of each other. So just because you have a blue one here doesn't mean it's more similar to the blue ones. Similar with the red pluses. And our 2 medoids, which are going to be our scenarios that we keep, they're not actually representing the space. You've got one down here in the cluster, which is fine, but you've got another one up off here. All right, so this clustering actually isn't really covering this space very well at all. So what you should do instead is transform to here and then cluster in this space, which is what I've done here. So you can see now we've got 2 clusters, but they cover different bits of the recourse space quite well. All right, so you've got all of these blue ones are quite similar, all these red ones are quite similar, and the representative scenarios we're picking, they're sort of along this like line here, which is much more representative. So you can see it's a much better representation of the recourse space, which again is the bit that we're actually trying to get to. So this is the key idea, is we don't care how similar 2 scenarios are in real terms. We care about how similarly they respond to a given first stage solution. Because if they respond similarly to a given first stage solution, particularly if they respond similarly to multiple given first stage solutions, we only need to plan for one of them, and we don't need to plan for the other one. So therefore, it's better to transform your scenarios to a space where the distance between them measures this distance in response to various first stage solutions. And we call this the recourse space. So yeah, so the old paradigm or the current paradigm of scenario reduction is you take your old scenarios, you do your scenario reduction on them to get your new scenarios. Our new paradigm that we're suggesting is you take your old scenarios, you take a bunch of candidate decisions, just some simple ones, I'll talk about how you get them in a bit, to get some recourse values, and you get recourse values for every candidate decision, every scenario, and then you perform scenario reduction on this. So then from that, you get your new scenarios here. So this is just like a step-by-step process of what I said. So you transform your scenarios to the recourse space. So the way you do this is you select a number of candidate solutions, and then you measure how each scenario in your large initial scenario set performs on each candidate solution. And you use this new space, which is the recourse space, to perform your scenario reduction method. So keep in mind, we're not specifying what scenario reduction method here. You could do clustering, you could do dimensionality reduction, you could do forward selection or backwards reduction. That doesn't matter. What we're saying is whatever you use, you should transform it to this space first. So I'm just going to have a quick slide on these candidate solutions. So ideally, your candidate solutions are quick to calculate because you do have to work them out beforehand. So if you have, like, if you're working out, I don't know, 100 of them and each one takes, I don't know, an hour to calculate, that's not really feasible. And then also they're of reasonably good quality, like they've got to be somewhat feasible. So you're actually testing these scenarios on reasonable solutions. So the way we've done it is we chose 50 candidate solutions. Each one we found by just randomly selecting 6 scenarios, just chose by random sampling and solving a stochastic program for that. Like I said, this random sampling isn't the best method in general, but for just getting some candidate solutions is quite a quick and easy method, and we find that sort of works well. So in order to sort of show that this idea works, we've done a bunch of experiments. So we're using 3 different spaces that we're sort of transforming our scenarios to before the dimensionality reduction. One is just a scenario space. This isn't transforming it at all. This is just doing our reduction on the scenarios. One's the opportunity cost space that I said some authors have used before. So that's the distance between 2 scenarios is the opportunity cost of preparing for scenario A and getting scenario B. This is a similar-ish idea to what we've done, except with their candidate scenarios, they're effectively only using 1 scenario to calculate it and not using multiple. Or the recourse space, which is what I've sort of been talking about. We choose 3 different scenario reduction methods. Oh, hang on. Sorry, a cleaner's in here. Sorry, 1 second. Okay, that's fine. We use 3 different scenario reduction methods. So we use K-medoids clustering. We use singular value decomposition. So that's dimensionality reduction. And we use Dubčekova's forward selection. And then we do this on 2 different problems. So we do this on a telecommunications network problem from Sen and some colleagues. And we do this from a stochastic service network problem, and that's from Hewitt, but this has come through at a few different ones. I should just say we had some problems doing Dubčekova's forward selection with the stochastic service network. We're getting some results at the moment which just don't really seem feasible. So I'm not presenting those because we want to look at those a bit more. But basically, so we've got these 3 methods for the telecommunications network problem, and we've got the first 2 for the stochastic service network problem. All right, and we're going to be looking at something called the outer sample stability. So that's kind of a measure of how accurately we're estimating the recourse function for that. So I'll just talk a bit more about this to explain these plots. So all of the results I present are going to be in the form of plots like this. So we're measuring what's called the outer sample stability. So what we've done is each of these plots is a different scenario reduction method. So this is K-medoids and a different problem. This is a telecommunications network problem. And so what we've done is we've taken this method with a given space, so the scenario space. We've applied the dimensionality reduction problem to this space for this number of scenarios, so that's 3. We've done this 20 times, so you get 20 different solutions. And then for each of our 20 solutions, we've taken 1,000 new scenarios, applied them to our solution, worked out the recourse cost and taken an average. So this spread is a spread of the 20 average recourse costs we got, applying this space with this problem and this method. All right, I do appreciate that's a lot, so let me know if that's the problem. So let me know, not let me know if that's a problem, let me know if that's confusing, like stick something in the chat or something and I'll explain a bit more, or feel free to ask a question at the end. But basically, what we're trying to look at is we're trying to see what the recourse cost is. So we want a lower value here. A lower value means a lower recourse cost. We're minimizing, lower is good. We also want a narrower spread in the box plot, because a narrow spread in the box plot says no matter how, you're more consistently estimating this recourse cost, even when you do this lots of times. All right, so now I've explained this, I can say what the plot's actually saying. So first thing you'll notice is as you increase the number of scenarios that you reduce your set to, all your solutions get more accurate. This is not novel or groundbreaking. As I said, this is sort of a fundamental tenet of scenario reduction. But what we do see is, particularly as your number of scenario goes up, using the recourse space has a lower median and a lower spread than using the scenario space or the opportunity cost space. All right, so this purple one, which is our method, is better than sort of doing nothing or doing what some other authors are doing as well. All right, so that's quite good. When we apply the SVD method to this to the telecommunications network problem, we see the same thing, particularly as a number of scenarios increases. That makes sense if you think about it. Like if you're only reducing your scenario set to one scenario, you've got kind of less scope to play around with picking good representative scenarios. So it makes sense that as you go more scenarios, like a more sophisticated method performs better. This plot's slightly simpler in that we did Duplikova's forward selection method. There's a lot less randomness associated with Duplikova's forward selection than the other methods. So with each of the 20 times, we found we were getting the same result the same set each time. So it's just a bar graph, but we do see that we're getting lower results as we're getting better results and lower costs as we increase our scenarios. We're now applying this to the stochastic service network problem, which is a different problem. In this problem, you can see it's a little bit less stable and the results are less clear, but we are seeing lower medians and lower spread as you get down to those higher values. And then we see the same with the SVD method. The SVD method, it's a bit less clear if we're beating opportunity cost. We're not doing worse than it, but it's sort of a bit less clear, but we are still getting a lower spread, which is nice. And on that measure with the opportunity cost, just one thing on the time taken for these methods. Obviously, scenario space doesn't take any time because you don't need to transform it. But using our method, the recourse space method, is a lot quicker than using the opportunity cost space. So even if we're only as good at it, which we seem to be in a couple of scenarios, it's a lot quicker. So yeah. Just a couple more slides on some limitations. So if you take a new scenario, so you've got a set of scenarios on, you want a new one, you want to generate a new one, you can't work out where that's going to fall in the recourse space. So if you recall this plot here, we've done k-medoids clustering because in k-medoids, the cluster center is an existing point in the cluster. Say you did k-means, and in this cluster, you're like, all right, the k-mean is somewhere in this white space here. So we want to pick a scenario in that white space there for our representative one. Well, you can't actually, keep in mind when you're creating your scenarios, you're doing it in the scenario space and you're transforming it into here. And there's no like nice transformation that takes it from the scenario space into here. So you can't actually tell where a new scenario is going to go. Therefore, you can't put a new scenario into the recourse space just where you want. So because of this, you've got to do this with scenario reduction methods. So you've got to have the scenarios that you're picking have to be existing scenarios in your set. You can't generate new ones. So I've said here optimistically, we've only tried it with scenario reduction methods. To be honest, we can't really think of a good way you'd be able to do it with scenario generation. The other thing I should say is that we've currently only tested this with network-based problems. And the mail center example, which we're going to move on to, is also, excuse me, a network-based problem. So we do want to use this with some other problems because maybe there's something about the network structure which lends itself to this. So just in summary, when you're reducing a scenario set, scenario similarity isn't as important as recourse similarity. We can use the recourse space to improve scenario reduction techniques. We've shown it's better than using the scenario space and the opportunity cost space for 3 different scenario reduction methods, particularly when you have larger reduced set size. And using the recourse space is also much faster than using the opportunity cost space. All right, thank you very much.